figure it out. So, I mean, nothing, it was great, it was ever done, it was great, it was easy. I mean, just if it was easy, everybody'd be great. But after you do it for a while, you guys really will get good at it. You are getting good at it. So, and the other thing is, I want, before you graduate, I want this stuff to come together to make sense for you. Now, I can tell you, most engineering students that have gone through programs, that go through the main campus programs, and for some of you that have come from the main campus, you know that it never comes together over there. Okay? For the most part, it doesn't. Because they've shot you with so many different things, but nobody's ever tried to pull it together. So every course we have, I want us to pull it together, which means if you don't understand, I want you to ask a question. Because if you don't understand, there's a good chance somebody else doesn't understand too. So I'm giving you the same old spiel over and over and over, but I'm doing it because, guys, I really want y'all to be good. I want you functioning at your full potential. Now, we have been talking about passive circuits. We haven't gotten to amplifiers yet. We've been talking about passive circuits. The circuits we have looked at up to today have all had a positive, the zero was positive, but if you actually located it, it would be a S plus a Z, okay? If you looked at your transfer function, everything we've looked at so far had a function like this. That your transfer function T of S may have something like this. It would have an S plus a Z. And down here it might be an S plus a P, which is a pole. Sometimes we want to change that. We want an S minus. Now remember, in the numerator, you can have minuses. Can't have them down here now. Get them down there, we're going to blow that thing sky high. It's okay. There will be times when you and I will design it so it is right on the verge of going to zero, this term here. But up top, we can have plus minus zeros up here on your zeros. This is a circuit that will give you a negative coefficient right here. It's a lattice circuit. You remember when we were taking circuits and we had lattices where you crisscrossed them, and so if you tried to solve it, it wasn't a real easy solve? Well, if I take that lattice, which I'm taking my input here and I'm running it to the output here, I'm taking my input here and running it there. So this is not a real easy circuit to analyze unless I flip it around and make it look like that. Now that one you can analyze, can't you? It's real easy to analyze. That will give you a negative coefficient on the top. Big picture, let's back up again. What are we doing? What we're doing right now is we're working with passive RC circuits only. Passive, no gain to it. And we're trying to learn how to determine the transfer coefficients and determine the poles and the zeros. In other words, if I need a zero at a certain point and a pole at a certain point, then what resistor and what capacitor do I put in there to make that happen? That's what we want to do. That's the big picture. This one's easy to analyze. And so what we want to do is we want to get the voltage between A and B. And it's easy to do that. You can analyze that really easily. And so we're going to do that. Okay? So the voltage, if I want this voltage V2 here, Jeremy, I sure wish you hadn't gotten that sandwich on. I'm now beginning to salivate.
5 points, you give it to him.
I was thinking about cutting class really short today. I'm going to have a sandwich. I haven't eaten lunch yet. Right? Sure does smell good, though. He was out there and he had a sandwich. It was that.
Oh my gosh.
He's already eaten it. No, you didn't eat it all, did you?
Yeah.
Things like that. All right. So V2 is VA minus VB. Now notice what VA is, voltage divider. Now it turns out in here that you can let those be any value you want to, but for our case we're going to let R1 equal to R1 down here. These two resistors be the same. We could let all three of those be the same. It really doesn't matter. It won't change anything other than just whatever value of R we saw for over here, we'd have to use it over here. So we're going to let them be the same. The voltage right here, VA, is 1/2 of this voltage here. Did y'all buy that? Sure, just voltage divided. So it's 1/2. The voltage right here, across R here, is going to be, again, voltage divider. It's going to be R times V1 divided by R plus 1 over SC. So then I can put all those together. I can put And I can rewrite it like this. And then I can put it in here and subtract the two. So this is that's my V2 or VB, and I'm going to put them together. So there they are. I'm going to combine them. Now, when you combine them like this, how do you get this out of this? And the reason I asked that question is I've had a number of you ask me, you're beginning to get hung up on how to go from something like this to something like this. Now, how do you do that?
Pull the V1 out.
Yep, I'm going to pull a V1 out of it. So then you'd have a 1/2 minus an SCR over SCR plus 1. And then what are you going to do next, Derek? Common denominator, right? So we do a common denominator. And when we do that, and I'm going to make sure I pull a 1/2 out too. So when I do that, that's where this comes from here. But notice what this is. This is a minus. So this has now moved and in the S domain, if we plotted it, here it is over here. And it's legal. Here's your 0. But don't do it with that one, with that pole. Make sure you keep your pole either right here. If it gets on that axis, it'll oscillate. Just sit there and oscillate. If you get it over here, it'll oscillate, but it'll die out. Okay? So, or it can oscillate and die out. May not have to, but it can. Okay, so let's run an example. We're going to let R1, right up here, equal to 2K, and R over here could be 1K, or we could make them all the same. We could let that be 1K or 2K, all of them be the same, but in this particular case I didn't. You're the engineer. See, it really doesn't matter what this value is here. You probably want it high enough so that you don't lose a lot of current through here. You don't want too much current flowing through there. And then so we'll just put those values in there, and let's run it. So if I put it in there, look at that output. What kind of output is that? It has a constant gain at all frequencies. How about that? Constant gain. Gain doesn't change. Now, if that's true, it passes everything. It's an all-pass filter is what it is. Everything comes in there. It passes everything. Of course, it loses half the signal. I mean, it loses 0.5. It's down to 0.5. It's more than 3 dB down. It's about 6 dB or so. So you lose it. But so why would you need one of these? Why would you need one? Because it's a way to hold a magnitude constant but change your phase. What if you were receiving two signals? One, we talked about this the other day, one from Atlanta and one from Birmingham, but you've got to sync them together because these two have to be synced. So you may want to change the phase on one of them, but you'd like the magnitudes to be the same, as long as the magnitudes are. So this is a way of changing the phase without changing the magnitude. So it's a neat little circuit. And I want y'all to just start putting these things into your memory banks. Real pleased with Sam Weigel the other day. He was coming to me and he's working on his project and he started saying, well, I could do he needs to do some filtering. He said, I could do an op-amp filter here and I could do this and this and this. And I was thinking, yeah, you sure can. That's great, man. He's using this stuff. The other thing, too, that I certainly want to mention to you, we had one of our senior design groups the other day was working on a project, and they want to. They're forced. No, they're not forced to. The company that they're doing this senior design project with constantly is pushing them to buy it off the shelf. Just buy it off the shelf. Now, again, I understand that that's what you're going to have to do if what you're doing is something someone else has already designed. But there's going to come some times where you're going to have to do the design yourself and you're not going to be able to buy it off the shelf. So I was really encouraging them, guys, you could buy this one off the shelf, but why don't you just design it? It was basically what it was a voltage regulator. It had multiple voltage outputs, and each one needed to be a regulator. And you can buy that. You can spend your $500 or $600 or $700, and you could build it for $25, maybe $50 at the most. So, the company is, we don't care, we just want one. Oh yeah, okay. So, but my point to you is, if you're not careful, you can quickly lose what we're studying. If you don't use it, you're going to lose it. So please, every chance you get as an engineer, use it. So that when they pay you those greenbacks, you can actually sleep at night. Because they're going to pay you good money. All right, and I just mentioned this. In each of the previous circuits, we have assumed that the load impedance was infinity. But do you realize that most of the time the load impedance out here is not infinity? It can be anything, 8 ohms, 100 ohms, 1,000 ohms, 10,000 ohms. So what we're going to do now, let's go ahead and look at adding the load back to those circuits that we were just working with. It really won't change anything. It just, it will change. Before, we would have looked at R1 and C2 without that load on it. But now let's just put that load back on it. So here's an example. And if we do, and we go back to our original circuit number 1. Circuit number 1 had a C1 across here, and it had a G or an R2 out here, didn't it? Well, let's let R2 be RL. And our C up here, how do you get rid of the C's? Make them go to what? How do you get rid of the C's? Now, when you're getting rid of the C's, what you're doing is you're putting an infinite impedance across here. How do you make a capacitor an infinite impedance? C goes to what? 0. Absolutely. So your capacitor goes to 0. It'll give you an infinite impedance here. And now we're just going to put the RL back on. If I do that, every place there's a G2, the G2 across here and a G1 up here. Every place there's a G2, I'm going to put 1 over R2. So right here, we're going to put, well, RL, 1 over RL. So notice this, and when you do it, straightforward, here's the transfer function that you get. Let's compare the two. Notice the difference. This is the transfer function assuming that your impedance out here is infinite. This is the transfer function assuming this RL. Will it change the two? Are they different? Yes, they are. They sure are. In fact, let's look at it. Let's do a little MATLAB and compare them. All right, so here they are. Notice what happened to the gain and the roll-off frequency. Here's your break point. This was the gain before we put a load on it. This is the gain after we put a load. Now the load, it may follow this curve right here and break out anywhere up here as your gain changes up and down this thing. But you can see how it drops the gain down. But it also does what to your bandwidth? It widens it, doesn't it? Okay? Sometimes, a lot of times what you may have is you may need to get this wider bandwidth, but you can't get the gain, so you just put another stage, put an amplification stage on that thing to get it amplified. So that's what we're going to do. Okay? And look at your phase. It'll shift you in phase as well. So here's your phase here. That was the original circuit, and now it's shifted over here by that. So you can, the load is very, very important. Now in your book, this is a synopsis. Now this chart here is for passive devices right now. Okay? We'll get into more active. But this K1 here is assumed to be a real value, and right now it's an attenuation. Later on it'll be a gain. We can add a gain to it. Notice what this first one looks like. It has a pole at 0. Okay? Here's what its magnitude looks like. Just dies out like this. Look at the phase. It's a constant minus 90 degrees. This has a 0, but no pole. The 0 is at 0, and it is a ramp. As the frequency increases, the magnitude of your transfer function increases, and your phase is a constant 90 degrees. This has a pole that's along the negative real axis. Look at this one. What kind of a transfer function is that? What kind of filter is it?
Low pass.
A low pass. Okay? Not a great one, but it's a low pass. And notice, you can see your phase is going down as well. And here is a 0. Okay? It's along the negative real axis. And notice what it does. It's going up like that. It's going to increase. This is both a pole and a 0, where the 0 is larger or more negative than the pole. So the 0, in this case, is bigger than the pole. And then you can see this thing is going to flatten this out a little bit here. And you can see how it changes your phase a little bit. This one here is a 0 at 0. And it has a pole down here. And notice how it goes up. It is a high-pass filter, isn't it? So that you might we might need to design one of those. Now look at this one. This one and this one is exactly the same, except what? What's the difference between this one and this one? Yeah, the poles and zeros have been flipped. So one here, for this one here, the pole is more negative. Nope, right here. The pole here is less negative than the 0. Down here, the pole here is more negative. And notice the difference between these two. What is the difference there? Absolutely right. One's a low pass and one's a high pass. Sure is. And you know what you can do sometimes on gain? Sometimes you can flip your resistors and capacitors around and it'll change it from a low pass to a high pass. That's all you have to do, just flip them. So every place you had a resistor, you put a capacitor there, and every place you had a capacitor, you put a resistor. And a lot of times it'll just flip around for you. And here it is where we have that negative 0 up here. And here it is that all pass filter is what it's called, but you can see that your phase changes. So what you want to do when you start to do a design, first thing you may do is say, what kind do I want? High pass, low pass, all pass, or maybe I want a ramp. What do I need? So then you go to this chart and you see this formulation here. So that's going to be the formulation you start with. And then what we have to do is come up with a circuit that can create these zeros and poles just exactly like they're presented here. So that's what we're going to do. Here's an example, problem 3.1b. Given, this is for a different reason. Given this function here, one of the first problems you were asked to do in chapter 3 was to denormalize something. So right off the bat, you don't know what it means because you didn't know it was normalized. Okay? I think we mentioned in chapter number 1 that you can take frequencies and your entire functions and you can normalize them. For example, suppose that your breakpoint frequency is really 1,000 hertz. Okay, here's my pole here is 1,000 hertz. It's really what it might be, this right here. If I take, so I have S plus 1,000, S plus 2,000 up top, right? All right. I can normalize this whole function by dividing both S and 2 and S of n, and 1 by 1,000. And what I've done is I've denormalized it. I've denormalized it to a value of 1. So my breakpoint now is at 1, not 1,000 anymore. It's actually at 1. So you can put this curve will give you the same response regardless of where the breakpoint is. It's going to look the same if you normalize it right. So the concept here, and the reason we do this is because, hey gang, suppose you know this is the answer you need, but it's not in the right breakpoint. So what do? You just normalize it. You come back here and denormalize this thing to move it over to the breakpoint that you need. Now in this particular problem, our original breakpoint was to be at 19K, right here. But this has been normalized. So it's not anymore at 19K, it's at 1K, or 1, just 1, okay? Now we do that a lot because in the text, a lot of the data that you're going to be given will be normalized to some particular, usually it's a frequency of 1, a breakpoint of 1, and then it'll have a capacitor and inductors and all that stuff that's been normalized as well. So how do I denormalize that function? If it's been normalized where everything has been divided by 19K, how do I denormalize it?
Multiply.
Absolutely all you do. That's all you do. Okay. So here's what's happened. I normalized it by 2 pi ELF, where ELF was 19K, and that gave me this S of n here. So all I have to do is come back now and multiply both the numerator and denominator by that value. So here's my value here, and so I'm going to come back and multiply both sides by this value here, or in other words, 2 pi times 19K, 2 pi times 19K. And of course here you don't really have to multiply that because you know that you're going to go from your normalized value back to your unnormalized value right here. If you multiply it through by 19K here, it would just eliminate that term right there. So that's all you do. Multiply top and bottom through by that value. Okay? And so now that's going to give me a 0 and a pole that's been shifted over. Did I lose anybody on that? Y'all see what we're doing? Because one of the problems will ask you to do that and it doesn't explain how you do it. But now you know. All right, so let's look at this. So here's my problem. We're going to find an RC model. You're the engineer, you need a breakpoint right here, and you need your 0 up at the top to be breaking at 2 pi times 19 kilohertz. So how are we going to do it? Well, we're going to start right here. Okay? And we may as well start there. That should give me values for a Z1 and a P1. So notice what I have. This was my worst case, or not my worst case. This is the most general case that you and I could have. And remember that when we solve for it, this 0 here is G1 over C1, and your pole here is G1 plus G2 over C1 plus C2. So what we have to do is we've got to choose a G1 and a C1 to give us that Z1 right there, don't we? Then once I've got G1 and C1, I've got to choose a C2 and a G2 to give me a pole right here, right? Got to do that? Y'all buy that? Okay. How many degrees of freedom do I have to solve this problem? How much information do you have at this point? You got 2 pieces of information. You got your 0 and your pole, right? But I've got 4 pieces of information here. All right? Okay. So that gives me 2 degrees of freedom. I can choose at least 2 things. So that gives you 2 opportunities to mess up. Right? So here's your S. Here's your Z up here. It's G1 over C1 or minus 1 over R1 C1. So there's 1. And then here's your pole down here. And here's what it looks like. Okay? Where K is equal to C1 over C1 plus C2. You're not worried about K right now. Unless they tell you what the K is that you have to have, and then that would give you some additional information that would help you solve the problem. But we don't, right now we don't have that information. So I've got 2 degrees of freedom to solve this problem. All right? Now, what are we going to do? So we look here, and here we look here, and we look there. Which one of these 2 functions do I have here? Z1 and P1. Which one of these curves will it look like? Why will it be the top?
Because it's S, like the one is normal is S plus 2, so it takes
All right, so he's saying the top one because he's saying that Z is more negative than the P, right? And you're right. You're exactly right. That's exactly right. And because we've got 2 up top here and only a 1 times this one down here, so you're right on target, Ty. That's exactly right. So this is what it's going to look like right here. Hopefully, we do it right.
And why Z again? Why Z1?
Because Z1 is 2 times as big as P1. See, 2 here, 1 there. And for this one here, John, that Z has to be more negative than that P there. In other words, Z has to be bigger than P for this to look like that. Okay? See how the Z, this is in the S plane. And see how that Z right there is bigger, more negative than that P? This one right here is 2 times this one here.
I looked straight up positive Z1 and I was like, wait a minute.
Yeah.
It's not.
No, you got to look at it as what happens when you solve for S. See, it's the S. What value of S will make that go to 0? And it'll be a minus Z1. Okay? All right. So now we have a low-pass filter because R1 is less than here. All right. So we're going to come back, and now we're going to choose 2 C's, and we're going to let both C's equal to 2 nanofarads. And then we're going to solve for the R's. Why 2 nanofarads? I don't know. Just choose 2 nanofarads. See if it'll work. If it doesn't work, well, you know. You got 2 degrees of freedom, so you might as well choose them. So we're going to choose 2 nanofarads, and we're going to put it in here. And Z1 then is going to become 4 pi times 10 to the 19th kilohertz, and that has to equal 1 over R1C1. So I can solve for R1. So R1 has to equal 2094. Right? Okay. Similarly, here's my pole. Now I know what C1 and C2 are, and I know what G1 is because G1 is equal to 1 over 2094. I just don't know G2. But look at G2. What's wrong with G2? Or what's wrong with R2? It's negative. You have a negative resistance here. Got a problem. So what am I going to do? Well, I'm going to go back and see if I can reduce down one of those degrees of freedom. I'm going to go ahead and use R1 and C1, but I'm going to let R2 go to infinity. In other words, I'm going to remove one of those degrees of freedom away. I'm just going to remove it. So now I only have to choose one value. I got these 2 chosen here, and all I have to do is solve for one of the values. So I'm going to remove one of those degrees of freedom because it's getting me in trouble. And I can do it by setting R2 equal to infinity. And so if I do that, and I come back and I solve for my R1 or my C1 and C2, let's see, is that right? I've got R1, R2, yeah, C2 is all I need to solve for. If I come back and solve for that, I get 2 nanofarads for this. And believe it or not, these 2 nanofarads will work if I just let R2 go to infinity, because I've kind of removed the degree of freedom is what I've done. Now, for you as an engineer, it may not always work like this, but you have to come up with positive values for all these. You're free to choose any value you want to, but you got to come up with some positive factors. And you don't want to have 10 to the femto farads back there, 10 to the minus 15th. You know, that's probably just your breath has more capacitance than that. So you don't want to do that. And you know, but you can let these go to infinity, so, or you could let some of your C's go to 0. But again, you're going to have to kind of play with that as an engineer. I don't know exactly which ones you choose and why you choose them. I mean, I'm sure there's probably logic to it, but I don't do enough work on that particular circuit to really know, and you won't either. You'll just have to cut and try on a little bit. Okay?
Was the 2 nanofarad selected or just part of the problem?
You'll select it. It was. And here you can see, here's your low pass filter. So it worked out pretty good. Most of the time we plot on the log using a Bode plot using log functions. So I just want to go back, since now that I know that you guys know how to do the Bode plot, I want to go back and remind you again one more time. Okay. If you have a function here, you got a function here, and these functions like this, I can take 20 log of this side here and 20 log of that side there, can't I? I can do both sides. When you take the 20 log of a constant, that's going to be this first term here. This is the term you're going to get. If you multiply in logarithms, if you have two functions that are multiplied together, you add their logs. If you have two functions and they're divided, you subtract their logs. So we've got this function here, and we're going to be adding this next function here because it's multiplied by this one. And we're going to have 20 log of j omega z1 over this. This is the magnitude of this right here is what I'm looking for. That's what those bars mean. And then I'm going to subtract 20 log of this bottom down here, this stuff right here. In terms of my angles, this k, this term here, has an angle of either 0 or 180 degrees. See, I can either have a minus here or a plus on that. Can't have any imaginary terms on that, so it'll be a plus or a minus. So it's going to either be theta k here is either 0 or 180 degrees. If it's minus, it's 180 degrees. The next term is I need the imaginary part over the real part of this next term right here. So here's my imaginary over my real. I could multiply this z1 through if I wanted to and normalize it out, and I'd still get an imaginary and a real part. So here's my inverse tangent of that. And then I'm going to subtract from it the bottom, the angle on the bottom, and there it is there. And that's what y'all have done. You did it in circuits, and that's what y'all played with a little bit in chapter number 1. So nothing magic with that. So let's look at each one of those terms. The first term, just as a reminder, if you take 20 log of this function here, it's going to be a constant value, and it's going to be a dB. It's just a constant. 20 dB, 28 dB, 16 dB, 3 dB, whatever. It's just a value. Its angle will always be either 0 or 180 degrees. If it's a minus, it's 180 degrees. If it's a plus, it's 0 degrees. So there's your first term. Second term. This is your magnitude, 20 log of this. Take your imaginary term here and square it, plus your real term over here and square it. And that'll give you your magnitude, and your angle again is omega over z1. And take the inverse tangent of it. And do the same thing for the last term. Now, let's look at this term here. Let's let omega go to 0 in this first term. We're just going to look and see what happens to it. Omega goes to 0. It becomes DC. And how do you evaluate a transfer function at DC? You let the frequency go to 0. And then you see what is the magnitude of that. And the magnitude of here is the square root of 1, 20 log of 1, 0 dB. So what it tells you is, at low frequencies, this first or the second term here, not your constant term, but the first term after your constant term, it has a 0 dB value when you're getting really, really low in frequency. You'll never reach 0 frequency, but as you do. And the angle on it is 0. Okay? Why? Because the imaginary term goes out and all you're left with the real term. So the angle is 0. Let's go to omega z over equal to 1. Now, what point is this right here? Omega over z1. What is that point? That is your 3 dB point, gang. That's your break point right there. That's when this omega z1 plus 1, that's when this omega over z1 becomes 1, and you got 1 plus j1, and you get the magnitude of that as the square root of 2, take the 20 log of the square root of 2, and it is 3 dB. So it's the same stuff y'all have been doing. This is that magic breakpoint that y'all seem to have a little bit of problems with. And it occurs when your imaginary term is equal to your real term. No matter what the real and imaginary terms are. When those two equal each other, and you solve for the omega for that, that's going to be your breakpoint. And the magnitude will be 3 dB. Your angle will be down 45 degrees. If you remember, 1 decade before this point right here, the frequency that will cause this point right here, 1 decade before that, this thing will start going down at a rate of 45 degrees per decade, so that when you hit the break point, you're at 45 degrees. What happens when you hit 90 degrees? It's going to flatten back out again, okay? And that's what happens when omega z goes much, much bigger than 1. When this term here is much, much bigger than 1 over here, this then will become omega over z1, and it'll basically be a straight line with a slope of 20 dB per decade. That's what this means here. It'll be omega over z1, and it'll either be going down at 20 dB per decade, or it'll be going up, meaning whether it's a 0 or a pole. The angle, as the frequency increases, and it's going to eventually approach infinity, okay, because that's omega here, there's an omega here, omega over z1. As this gets bigger and bigger and bigger, this is going to approach infinity, and the inverse tangent of infinity is 90 degrees. So, using a straight line approximation, that's what it looks like. Starts over here at 0, comes over here, breaks here, this is your 3 dB point, starts going up at 20 dB per decade. If you and I plotted it, here's what it looks like. Comes over and starts going up. Now, what about this angle down here? How's this thing going to work in terms of angles? 1 decade before the breakpoint frequency of 1, it's going to start doing what? It's going to start going up or down 45 degrees. In this case, it's going to go up 45 degrees. So it's going to start going up at 45 degrees per decade, so that when it hits this point right here, what will it be? 45 degrees. Then it come on up here to 90, down here, and level on off. Okay? So there it is there. Y'all remember that? Okay. Now, the only difference between this and having a pole is that it's just negative, all this stuff. So if you came back and here's the actual plot, remember that this thing does not follow straight lines. This is 3 dB up by this point right here. So it starts here and it starts going up like that, about 3 dB, so that here you're off by 3 dB. But most of the time, you and I can just draw it here like that, draw the straight lines, and then kind of sweep it up there 3 dB, we're pretty close. But if we wanted to flip around the other way, and now this is all this is the pole. It's just, but it works exactly like the 0, except it's going to go down. So it's exactly the same, except it goes down. Remember, it comes over here, it starts at 0 dB, it comes over here. At the break point, it starts going down 20 dB per decade, or minus 6 dB per octave. We don't work in octaves. Unless you're a pianist or a vocalist. And you can see what it does. It comes up 1 decade before, it starts going down 45 degrees per decade, gets 45 here, goes over 1 more decade, levels out. All right, everybody remember all that stuff? Yay, nay, somewhere in between. Yes, you do. You can do it. Y'all spend lots and lots of time on this. So I feel like you have it. Besides, we need to continue this on so we can eat some. Absolutely.
Sandwich.
Hunger pains begin to overtake me. It's Jeremy's fault. All right, we want to plot this transfer function here, right here. Now, it's not in standard forms. I mean, you know what it is. You know what the breakpoints are, but it's not in standard form. So let's put it in standard form. Put it in standard form. I'm going to pull a 0.5 out, and we'll pull a 3 out. So here it is here. When you pull those out, what you do is you divide everything over here by 0.5. And here, when I divide it by 0.5, I get a 1. And here, when I divide it by 0.5, I just get a 0.5 in the denominator part of this. And here, when you pull a 3 out, you divide everything by 3. So your S's, or your J omega is divided by 3, plus 3 divided by 3 is 1. So there it is there. By looking at that, can you tell me what the breakpoints are? All right, your 0 breakpoint is 0.5. Your pole is 3. So one's going to be going at 0.5, one's going to start going up at 20 dB per decade, and it's going to keep on going forever and ever and ever and ever and ever and ever and ever. But when you hit 3 dB, the frequency of 3, omega for 3, it's going to start going down at 3 dB per decade, and it'll level at the 2, then cancel out and then level out. Okay? So if you take the log, 20 log of 0.5 over 3. You take 20 log of that. I think you get something like about 15 minus 15 dB or something like that. I think. So I should have. So to that, I need to add 20 log. Well, here it is. Here it is. Here. This one here is about minus 15 dB, I think. And then to that, I'm going to add this one, and I'm going to add that one. Each one of those will start their action at 0.5, and then the following one will start at 3. So, and my angle starts off at 0, because the angle here for my my constant term had no negative on it, so it's 0. And then I'm going to do the inverse tangent of those two. So, if we plot it, there you go. All right? Now, the constant is minus 15.6 dB is what it is. There's a constant down here at minus 15.6 dB right here. It's just not shown on this top. Then you come along here and at 0.5 your 0 starts. And it starts rolling up here and it goes on forever at 20 dB per decade. When this one is, your pole is coming along here, and when you hit 3, it starts going down. And remember, you superimpose the 3 of those together. And when you do, this is what you get. It starts at minus 15.6 dB, goes over here, and it starts going up at 20 dB per decade. And you hit 3 over here, then it's going to level back out because that one's going down at minus 20 dB per decade. And then you could add the angles and do the same thing with those. Okay? So everybody's got it. So I could give you a quiz right now, and y'all could make 100 on that thing. Right, huh? Sure you could. Wrong. John says, no. So I need to. You need to process a little bit. Well, but y'all do remember all the stuff. You don't remember, John? That's true, John. John, you did. Who was your instructor?
I believe
We could.
Deep wounds come up with that one.
I know. Okay. Well, all the others know how to do it. Yeah, absolutely. This is the class of 100s and hopefully all A's. Okay? All right, notice now, I should have done this in log and I didn't. But the 0.5 over 3 is about 1.166 in magnitude. Here it is right here, 0.166 right there. And you can see that it's going over here, and then all of a sudden at 0.5, this thing's going to start going up over here. When it starts to go up, it goes up to 20 dB per decade, and then when it hits over here about 3, it's going to pull it back over and level it back out again. So there's that's the old wonderful MATLAB wonderful curve. So there it is there. Yes, guys, I'm sorry, but I'm going to have to take a quick one today. So here's yes, we are. Yes, we are. I was going to go past this, but I really shouldn't because that says stop, and we're engineers. What it says. And we really do. Yeah, I know. Okay, but here's your. Yeah, I got to go eat, man. I got to go eat.
Wow, now I know to bring this glass.
All you have to do is if you bring Subways to me, it might work better. All right, listen, I'm going to let y'all go because I really have to go eat. I have a slight blood sugar problem that will start causing problems in my head.